We're going to do a couple more examples of modeling with exponential functions. And so here we have a situation kind of similar to the ones we were looking at earlier this week. An invasive fish species has taken over a lake. 5 years ago when this started, there was 20 of this species of fish. And now there are 22,000. So this has increased pretty quickly. So what it asks us to do is write an exponential function f of t that models the fish population t years after the fish were introduced. So here's what we've got. We know the number, we know the original number of fish was 20. We know that after 5 years, we end up with 22,000. What we don't know is we don't know the rate, the relative growth rate of these fish, or of the fish population. So here's what we're going to do for f of t. First thing we're going to do is just plug in this 22,000. And then we're going to build the function like we normally would. Start with our initial amount, the 20. And then we have e. And then remember our exponent for this type of function is rate times time. And we don't know the rate right now, so we're going to use 5 for the time, because 5 corresponds to 22,000 fish. So we're going to say 5 is our t, and then multiply that by the rate, which we don't know. So what we need to do first here is figure out what is our rate, what is our relative growth rate. Once we have that, we'll be able to write our function. So as usual, we're going to divide by the initial amount, divide by the 20. When you do that, you get 1,100 equals e to the 5r power. And because it's e, we will take the natural log of both sides of the equation. And as always, that allows us to take that exponent and pull it out front. So we've got natural log of 1,100 equals 5r. Our exponent goes out front times the natural log of e. And again, natural log of e is just 1. So that cancels out of our equation. And so now we have natural log of 1,100 equals 5r. All we need to do to get r is divide both sides by 5. When you do that, you end up with 1.4 is equal to r. And I want to be really clear what this means. Remember when we do rates on these problems, we always move the decimals 2 places. So for example, if we wanted to do 5.6%, when we put this into the function, it would be 0.056. We always change it to a decimal. So 1.4 is the percent after it's been changed to a decimal. So if you think about what that means, if you move the decimal back 2 spaces the other way, this is going to be 140%. And so what that means is these fish are growing at an alarming rate. So after 1 year, they would be at more than 100% of their population the previous year. Or they would add more than 100% of the previous year's population. So they're more than doubling every year, basically. Okay, anyways, we know r is 1.4, so now we can write the function. So we're going to go f of t, so number of fish after t years, equals the initial amount, which was 20, times e, and then our exponent is rt, rate times time. The rate is 1.4, we just discovered that, and then t is our variable. So 20e to the 1.4t, that's our function. Now the second part of this, we just have to plug in. We got to find the fish population 10 years after they were introduced to the lake. So let's go ahead and do that. Using our function here, we just plug 10 in for t. So we have f of t equals 20e to the 1.4 times 10 power. We can simplify that a little bit. It's 20e to the 14th power. And when you plug this into a calculator and get your answer, you're going to get 52,086,000 and 86. So A lot of fish. So chances are something's going to happen at some point to keep this fish population from growing at this rate, because there's only so much room in a lake. But right now they are growing at an alarming rate. And after 10 years, you end up with over 24 million of these fish. All right. So the new thing there that wasn't a part of the problems we did last time was finding the rate. But as you can see, it's pretty much the same as when you're trying to solve for the time. You're using that logarithm, taking a log of both sides to be able to isolate the variable. So next one I want to do is similar, but a little bit different. There's one more wrinkle added in here. Here we have this endangered snail species. Its population has been declining since 2000. In 2004, the population was 8,000. And by 2007, the population was 6,400. So here, we don't have the rate again, but we also don't have the initial amount. We don't know how many, because remember, we're starting in 2000. We don't know how many snails there were in 2000. So the first thing we're going to do is we're going to go ahead and find the rate. And to do that, we are going to kind of shift our situation. Instead of starting in 2000, which we can't do because we don't know the number of snails, we're going to start in 2004. So for this, 2004 is going to be year 0. And so that's going to be our initial amount, is the 2004 amount. The other thing we know is the 2007 amount. So in this situation, 2007 would be after 3 years. So that'd be year 3. So here's what we can do. We can say after 3 years, we have 6,400 snails. Our initial amount for just this part of the problem was the 2004 amount, which is 8,000, because that's the oldest amount we have. That's as far back as we can go. Then we have E. We don't know our rate. That's what we're looking for. But our time here is between these two numbers, between these two amounts, we have 3 years have passed. So our time is going to be 3, and then we don't know the rate. So similar to what we just did, we're going to divide by this amount. You will get 0.8 when you divide that, equals E to the 3R. Once again, we'll take the natural log of both sides. So natural log of 0.8 equals natural log of E to the 3R. This allows us to bring 3R out front. And then ln of E cancels itself out, and we just divide by 3. So you have ln of 0.8 divided by 3. That's what you would punch into the calculator. When you do that, you get approximately negative 0.074. So approximately negative 7.4%. And so keep in mind these are exponents. So a negative exponent is not going to mean negative snails. What it means is the amount of snails, what the snail population is getting multiplied by, is a number less than 1. So that's going to make the total number of snails go down. It will still give you a positive result, but it's going to be a smaller result than what you had started with. So whenever you're dealing with decline or decay, you should expect to get a negative number for your rate, because the exponent's going to have to be negative to make that work. So that is the type of number we should get, and so that's our rate, is negative 0.074 or negative 7.4%. Now we want to find the number of snails in the year 2000. 2000 here is our initial year. That's when we're starting. So what we want to do here is we want to pick one of the other 2 years, and it really doesn't matter which one we do. I'm going to go with the 6,400, the 2007, but you could just as easily do this with the 8,000. It really doesn't matter, but pick one of those. So I'm going to start 6,400. So remember, that's snail population after 7 years, equals, here we don't know the original amount. So that's what we're trying to find. And the way that's usually written is n sub 0. but you could put any variable you want there. It doesn't really matter. So that's our initial amount, and then times E. And then we have, again, to the RT power. So R is our rate, which we just found. That's negative 0.074. And our T here, because I went with 6,400, that's the 2007 number. So that is 7 years. We are in, this is year 7 amount. So I want to use 7 as my T. If you were to use the 8,000, that would be 4 years after 2000. So you'd use 4. So there we go. So I have E to the negative 0.074 times 7. And the nice thing here is to figure out the initial amount, all you have to do is divide 1. So you don't have to do any logarithms. So what you do is you divide by E to this exponent to cancel that out, and then that's going to give you your answer. So when you divide that, when you punch that into a calculator, you get approximately 10,743 snails. So when they noticed this decline in the year 2000, there were 10,743 snails of this species. By 2004, it was down to about 8,000. By 2007, it was down to about 6,400. So now the last thing it says to do is to write a function for the number of snails t years after this starts. So now we have our initial amount. So it says t years after 2000, so we need to start with the amount in the year 2000. We have that. We know the rate at which the snail population is declining. And so that should give us everything we need. So we're going to do S of t equals the original amount, the 10,743, times E. Then our exponent is the rate, times the time, and time is our variable. So that is the function we could use to be able to estimate the snail population at any point after 2000. So there you go. That's the 2 additional examples for this next assignment.